All right, so a reminder about our guidelines to solve optimization problems. Remember, you're looking for where a min or a max occurs, looking for the optimal situation. So the first thing you want to do is think about everything that's given to you and what you're looking for. Draw a sketch if applicable. Sometimes your helper information comes from that picture. We're going to write the primary equation, and that'll be the one that gets the calculus, right? So we'll take the derivative of that equation. We're going to get the primary equation into one independent variable using some sort of a helper equation. We're going to talk about the feasible domain because these are all real-world problems, so we want to make sure that our numbers make sense. And then we're going to actually make sure that we are answering things within that domain, but more specifically also checking that our answer makes sense using our calculus techniques. All right, so our first example, it says find the point on the graph of f of x equals x squared that is closest to the point 2, 1/2. So here's our coordinate point, 2, 1/2. And what we want to find is what point along this parabola is the closest or the shortest distance. So any one of these points, it doesn't matter which one I pick, any one of those coordinate points is going to be x, f of x, in which case for us, it's x, x squared. So what I'm really trying to do is minimize the distance between that green point and any one of those black points, okay? So I'm trying to find which of those black points is going to be the one that is closest. So in minimizing the distance, I'm going to start with the distance formula. Distance equals square root of change in y squared plus change in x squared, which is really the Pythagorean theorem, which is also the equation of a circle. A lot of connections here to geometry. So let's use our helper equation, which is this information, also our picture could be considered a helper, and get this distance in terms of one single variable. So I don't want to have x's and y's anymore. I want to just have a single variable. So one of my coordinate points would be in goes 1/2 for x, and out comes 2. The other coordinate point is from our helper, in goes some x value, and out comes x squared. Okay, so I need to minimize this distance, which means I need to take the derivative of distance. Well, one way I can make taking the derivative just look a little bit nicer is using a rewrite with exponents. And then I'm going to actually clean up the inside as well using algebra. So I'm going to square some stuff out. X squared minus 2 squared gets me an x to the 4th function. This x minus 1/2 squared gets me an x squared function. I want you to take a second, pause the video, and go ahead and expand this out. Get one trinomial inside of here. Pause your video. All right, I came up with x to the 4th minus 4x plus 4.25. So the next thing then is I'm going to take the derivative. So in taking the derivative, this becomes d prime. I'm going to swing the 1/2 down. Leave the inside alone, drop the power. Times the derivative of the inside, which will be 4x to the 3rd minus 4. All right, well, rewriting this so I can figure out where this derivative is equal to 0 or where this derivative is undefined. Here's my d prime. So 1/2 times these 4's end up with 2. So 2x to the 3rd minus 2 in the numerator. In the denominator, we get the square root of x to the 4th minus 4x plus 4.25. So I'm going to set this derivative equal to 0, which remember our shortcut is that we take the numerator equal to 0. So this will be x equals 1. And I want to set the denominator equal to 0 because I want to consider if this was ever undefined. If you were to graph this or try to, you can't factor it, but if you're trying to use synthetic division, long division on it, you end up that this will never be equal to 0. So this doesn't equal 0. We're never undefined. Something to consider is our feasible domain, right? So I could do a second derivative. I could find d double prime and sub in 1 and figure out what I get, but this is not something that's friendly to take the second derivative of. So I'm going to use the first derivative test, which means I need to consider on this number line, what are my restrictions? So I know 1 is critical. Let's think about what other x values we could have. Well, I think we can agree from the picture that anytime that x would be less than 0, anything in the second quadrant is definitely not going to be close, right? So I'm going to set our feasible domain to be somewhere between 0 and infinity. We want to look at parts of this parabola that fall in the first quadrant. So I'm going to throw a 0 on there. Let's test a number. So if I pick a number between 0 and 1, then this numerator ends up being negative. If I pick a number between 1 and infinity, this numerator ends up being positive. So we have found a minimum at x equals 1. Remember, we don't have to test endpoints because we're not on a fully closed domain. So we'll have a minimum distance at x equals 1 because d prime changes from negative to positive. This question, though, asks to find the point. So I know the x value is supposed to be 1. My y value then, if I use my helper, right, we use the helper to start the problem and to close the problem, I need to find f of 1. Well, that's going to be equal to 1 squared. So it's the coordinate point 1, 1. That's going to be the shortest distance from the coordinate point 2, 1/2. All right, that is how we use the distance formula. So again, distance is our overall primary equation. We're using the helper of our picture slash the given information of x, x squared. This is just chain rule derivative happening here. And I chose the first derivative test to verify because the second derivative test would be very messy.